Hey everyone, and welcome to our next lesson in Unit 5. Today's lesson is going to focus on electrons and light, and specifically how electrons and electron transitions can produce different photons of light, and we'll focus on specifically the visible wavelengths of light that we can see. So after today's lesson, you should be able to identify an element by comparing its bright line spectrum when given other spectra of other elements, and you'll be able to explain how excited electrons give off energy in the form of light. So we'll start our lesson about electrons, where we will take into account our model, our cloud model, and the various energy levels that electrons can lie in. And we know that electrons surround the nucleus in distinct energy levels, and these energy levels have specific energies, where we have higher energy electrons farther away from the nucleus and lower energy electrons closer towards the nucleus. And each energy level, as the ring gets bigger, as we move out from the nucleus, can hold an increasing amount of electrons. So our first energy level closest to the nucleus can only hold 2 electrons in one orbital, and as we move out to the second energy level, we can then hold a maximum of 8 electrons, and down to the third, we increase that number even more, and the third energy level can hold a maximum of 18 electrons. And if we go down to the fourth, we can hold a maximum of 32 electrons, and so on. Now, electrons like to lie in what we call the ground state, where all the electrons are in the lowest possible energy level. And on your periodic table, we can find that ground state electron configuration in the bottom left of each of the entries on the periodic table. And this notation is going to indicate in what principal energy level electrons are lying in. For example, in magnesium, we have 2 electrons in the first principal energy level, 8 in the second, and 2 in the third. And that's going to be considered the most stable location for electrons in that particular element. Now, if we give an element or an atom or electrons energy in the form of light, heat, electricity, or what have you, electrons will absorb that energy and jump to a higher energy level. This is called an electron's excited state. They get excited by gaining extra energy. And with that extra energy, it makes the electron and the atom that it's with unstable. Now, this will be any electron configuration that has an appropriate number, the correct number of electrons for that particular atom, and it doesn't match the configuration from the periodic table, which would be the ground configuration. Now, electrons, we'll see in this little simulation here, we have 2 electrons and 2 energy levels with the nucleus represented on the left. Now, if this atom absorbs energy, or the electrons absorb energy, they can move to that higher energy level, and they kind of jump up to that next energy level. This is unstable. Higher energy levels are considered unstable. So the ground state configuration where we started would have been 2 electrons in the first level. But the excited state configuration changes to 1 electron in the first level, 1 electron in the second level. So we have the same number of electrons, but it doesn't match the ground state configuration. So therefore, it's considered an excited state configuration. Now, we know opposite charges attract. Electrons are attracted to the nucleus. So excited electrons, when they're given extra energy as they jump up to a higher energy level, once they lose that energy, they are attracted back to the positively charged nucleus and go back or fall back into their ground state. When they fall back into their ground state, the energy that they had absorbed to jump up to a higher level then gets released from the atom as the electron falls back to its lower, more stable energy state. So the electron that had absorbed the energy falls back down, and then we get energy release. Remember, we don't create or destroy energy, so energy gets released, and when it does, that energy has to go somewhere, and that energy we see as different colors of light. So as the electron falls back down to a lower energy level, a photon of light will be released from the atom. Now, depending on how much energy that the electron had initially absorbed and on how far it's going to transition to its ground state, it's going to release a varying amount of energy, and we'll see that in different forms of light, oftentimes in the visible range, but also as well in ranges that we can't see on the electromagnetic spectrum. Now, the energy that's being released from these electrons is released as packets of energy that we call photons, which are essentially massless and the smallest known particles. And they are going to travel at the speed of light, which is a extremely fast value of 3 times 10 to the 8 meters every second. Now, the color of light that an object is going to emit is going to be determined by how much energy was initially gained by that electron and therefore lost when the electron dropped back down to the ground state. So whatever quantity is being absorbed is the exact quantity that is being released. Now, more energy means that we have a shorter wavelength, like gamma rays, X-rays, and ultraviolet. Medium energy is going to fall in the visible light range, which we can see, and the lowest energy are going to be longer wavelengths like infrared, radar, microwave, and radio waves. Now, if we imagine here, we have a little setup where we can, using electricity, kind of fire electrons at this atom of hydrogen here. And I'll point out a couple things. And I'm going to run this simulator in slow motion so you can see this a little bit better. We have different energy levels. 1, 2, 3, and 4, 5, and 6 are kind of overlapped here. They're much closer together. We have a big gap here between the first and second, which is a big energy difference here. Now, if we excite this single atom of hydrogen by passing electricity through it, hydrogen only has 1 electron, and we're going to see this electron gain energy, and it's going to jump up to the second energy level. We'll see what this looks like. This is going to happen pretty slow, so we have the energy of the electron here. It's absorbed by that atom. We see the electron in hydrogen jump up to the second energy level, and then we see this photon being ejected. And I'm going to run this again here. We see this kind of purplish looking photon coming off, and that happens, see if I can catch this right. The electron jumps up. When it falls back down, that's when we have that photon being ejected. This difference here from the first to the second is causing a photon, we can see from our spectrometer, is forming in the far ultraviolet range of our spectrum. And if we run this continuously, or we keep firing, I'm going to not run this in slow motion, or we keep firing many electrons, we start to see all these photons transitioning. And we're seeing lines start to form every time we have one of those photons released in the far UV portion, and we're starting to see a purple line forming here. And that's from a different transition. We saw the transition from 1 to 2. The photon that gets ejected here is forming in the far UV, and then we have another collision happening, or excuse me, a transition that's resulting from a higher energy collision, and we're seeing a electron jumping up to the third and falling back down to the first. And we'll do this in a couple different forms, but you can see, and we can increase this, we're seeing a different transition happening there, and each time it happens we're getting another little tick when we see that kind of violet photon being released here. Now, if we increase the voltage on our battery and give this atom more charge, we're going to see that electron jump up higher into a higher principal energy level. And each time we're getting these different colored photons that are falling out. Because as this electron jumps up and gains energy to go to the third or fourth energy level, it's a higher energy to fall back down. Therefore, it's going to change what color photon we're going to see. And as these transitions happen over and over and over again, we start to see this fingerprint of hydrogen occur. Now if we lower the voltage and we don't excite that electron enough, it's not even going to jump out from its ground state. It needs to have a certain amount of energy in order to be ejected from the ground state and to jump up to a higher energy level. So this has to be set to a certain point. We have to have enough energy in order to cause that transition from the ground state to a higher energy level. Now if we do this with multiple atoms, again we'll look at our spectrometer here, which is going to indicate all these photons that are being ejected from these multiple atoms of hydrogen, and this is occurring constantly. So we'll increase this a little bit, and down here we can see all the electrons that are in the simulator here and the transitions that they're going through. They're getting excited, they're jumping up to the second, fifth, sixth, we don't really see too many in the third, a couple in the third, a couple in the fourth, and then they're falling back down, and we're seeing these different colored photons being released. And over time, we're going to start to see a specific fingerprint that we'll find is unique to hydrogen, because all the electrons that are in hydrogen can only have a certain number of different routes that they can take when they're energized. And this, what we call bright line spectrum, is going to be unique to elements, and we can use it to identify elements in an unknown sample. Looking at the periodic table here, if we want to look at hydrogen's bright line spectrum showing all the electron transitions in the atom, well, it's going to be similar to what we're seeing lining up here. Now this is only showing the visible changes. We have 4 bars there, and we're seeing 4 bars here, colors slightly different. We're not seeing the far infrared or far UV transitions because, well, we don't see them with our naked eye. We can't see that portion. We can only see the visible light. So this is the portion that we're including for a particular element. And it's going to be unique to the element. And it's going to change depending on where they're located on the table, how many electrons they have, and how those electrons can transition between different energy levels. Now comparing this, or an unknown sample, to, let's say we wanted to look at, let's see if this sample has any traces of carbon in it, we can look for these specific bands of light at these specific wavelengths and see if that sample contains any carbon. And these, again, will be very different from each other. Some are a little bit simpler, and some can be kind of hairy. Very pretty, though. Now a little bit about light waves themselves. We measure them in energy, which is measured in joules. We can measure the wavelength between waves, otherwise known as lambda, which is measured in meters. We can measure the frequency, represented by nu, measured in wavelengths per second, how many wavelengths are passing a particular point, and the frequency and wavelength and energy are all associated to each other. And all photons of any type are going to travel at the same speed, which is the speed of light. So light that has a shorter wavelength is going to have a higher frequency, and vice versa. And we'll take a look at what that means on our graph here. So higher frequency, meaning more waves are passing a point at any particular moment, means we're going to have a shorter wavelength. And a wavelength is the difference between 2 points on a wave that are 180 degrees from each other. So we can compare crest to crest at this point. The closer those get together, the higher the energy of the wave. The farther apart they are, the lower the energy of the wave. Lower frequency means that we have fewer of these waves passing a particular point. Shorter wavelength means we have a higher frequency. More of these waves are passing a particular point because they're closer together. Radio waves have a longer wavelength. They are considered low energy. Gamma rays, shorter wavelength, are considered higher energy. Visible light's going to fall right in the middle here. We can see that the wavelength falls kind of in the middle of all of these, and this is the part of the spectrum that we can see. We have interactions with microwaves, radio waves, infrared waves, as well as our higher energy radiation, ultraviolet, X-ray, gamma ray. These are the ones that we try and stay away from. These are the ones we can see, and these are the ones that are useful in a lot of different ways that we use probably every single day, but aren't really going to cause problems with our biology. Now those excited electrons that we saw in the simulator have particular choices. Once they get excited, they can drop back down to the ground state in several different pathways. If they jump up to the third, they don't have to drop from the third to the first. They can drop from the third to the second to the first. And if you jump even higher, let's say you jump up to the fifth energy level, there's a lot more different pathways that you can follow. You can fall from the first to the fifth, fifth to the fourth to the first, fifth to the fourth to the third, to the second to the first, and so on. But each drop in energy, our energy level, is going to give off light with a different amount of energy and therefore a different wavelength. Sometimes we'll see them, sometimes we won't. But we can take the transitions that we see in the visible spectrum and form what we call there the bright line spectrum, which is specific to each individual element. Now this diagram is kind of showing that if we jump from an energy level of 2 up to 6, the transitions here, let's say from 6 down to 2, is going to be in that violet or higher energy range. Now we're going to see some lower energy wavelengths in our red and green, and that's going to depend on the transition as that electron drops, depending if it's from a higher energy level or maybe one that's a little bit lower, like a 3 or 4, back down to our ground state. And this can happen over a couple different transitions using a couple different photons. We might see an electron go from 2 up to 6, and we may see a blue and red, or let's say a green and red photon given off as this transition happens in multiple steps. And again, this will depend on the atom and how it is being excited. So what we looked at there for each element was a spectrogram. And by exciting the gas of any element with an electrical charge, we can see all these different pathways that electrons will follow by constantly giving that sample energy. And breaking up the light that's being given off by these atoms shows the different individual energies. And we do this by using a prism and a spectrometer, which breaks up the light being given off all at the same time into individual bands of light, and that's what we saw in those bright line spectrum. And no two elements are going to have that same bright line spectrum, and therefore we can use what we know about, let's say, hydrogen and helium to identify those elements in a sample of unknown. And these will be specific, so every time we see a bright line spectrum of hydrogen, it should look pretty much just like that. If it's not, we might have impurities or something along those lines, but it's always going to produce the same kind of fingerprint. And if we're looking through a spectrometer, let's say to a distant star or something in the universe, we can actually see these spectra being emitted from celestial objects, stars and other things. And we can actually see that, okay, from this star we're seeing hydrogen and helium and maybe some other things that are emanating from that light source by looking at it through a spectrogram. Now we do see this in the real world a fair amount, really anything that's being producing light. So specifically, as we just talked about, spectral analysis of stars, seeing what elements are in stars. Fireworks that are producing these colorful lights are being produced in this way. Flame tests, which we'll do in lab, are done the same way. The colors in fireworks are produced from the electrons of different elements in those fireworks as they get excited. Remember, we have to ignite a firework. We give it a small activation energy. We have a reaction that occurs, and as those electrons and those atoms of those elements in those fireworks get excited and they transition between the ground state and an excited state, we're seeing these photons of light being given off. So the colors here are going to indicate to an extent what types of elements we're using. Now we'll take a look at this specifically in lab and see what different types of elements, what colors they'll produce, and how we can break that up using a spectrometer to look at an element-specific bright line spectra and compare it to unknown samples. If you guys have questions on any of this, make sure you come see me and get your questions answered. Hope everyone has a great day.